Hello, everyone. My name is Frank Efe. I'm here to share my research on the growth of iron platinum thin films grown by magnetron sputtering. Um, yeah, my research workflow um, goes from introduction, literature review, research problem, objective of the research, contribution to knowledge, methodology, result and discussion, and lastly, conclusion. Introduction. Iron platinum thin film is a thin layer of ferromagnetic material whose thickness ranges from a few nanometers to about 10 micrometers. And this material has similar properties with the bulk material, although they are modified. They're modified by the method of preparation, and they also have a large surface area to volume ratio. Why the need for this material? Because we are trying to reduce the complexity of our electronic devices. That is, we are reducing the bulkiness of this material. For instance, last decades or 50 years ago, nobody believed there would be something like Apple Watch. So we try to reduce the component of this, the size or the bulkiness of these electronic devices to miniature devices that can be handy. So iron platinum has various interesting properties ranging from huge inertial magnetostriction and magnetic anisotropy, large magnetic moments, tunable properties, and thermal chemical stability. Various researchers have delved into studying platinum because of these interesting properties. As a result, um, it serves as promising material for device fabrication, especially in memory device application. Some of the materials we can find is thin film or application of this thin film ranges from uh, we have the speaker, we have the memory disk storage devices, and the likes. The motivation of this study entails changing the orientation of these spins or magnetic domains from longitudinal magnetic moment to perpendicular magnetic moment because we are trying to enhance or increase the storage capacity of our electronic devices or memory devices. Now, figure 2A shows the configuration of longitudinal magnetic moment recording, and we could see the spin alignment, which gives room for a little amount of data storage for this particular configuration. However, in figure 2B, we could see the alignment of the domains of bits in perpendicular manner or configuration, which gives room for more data storage. That is, it increases the area density of this material. And figure 2B to figure 2C shows the lattice arrangement or configuration of iron platinum. Now, iron platinum, like I said, has several interesting properties. They exhibit two different configurations, that is the L10 phase, that is the FCT phase, face center tetragonal, and the FCC phase, that is the soft phase. Now, in the soft phase, the iron and platinum are orderly arranged. That is, at this region, we could see the iron atoms at the corners, while on the faces, we have the platinum atoms. However, for the um, for the soft phase magnetic properties of this material, we could see iron atom at this corner, platinum atom at this corner, iron atom at this corner, platinum iron at, that is, the atoms are irregularly arranged in the lattice structure. Several researchers have studied this material. However, there's still a knowledge gap in reporting why we have double switching properties in iron platinum thin film deposited on silicon substrate. The difference between this established result or research and mine was I varied the temperature. We studied the effect of temperature on this material, and also we tried to investigate what are the causes of the double switching properties of iron platinum on silicon substrate. Research problem. Various techniques have been used to grow iron platinum thin films to achieve an ordered L10 phase, that is the phase F60 phase. However, the study of double switching properties in iron platinum thin film on silicon substrate has not been reported. Hence, we deposited and characterized iron platinum thin film on glass, silicon wafer, and oxidized silicon through DC magnetron sputtering device, and investigated the occurrence of double switching mechanism on silicon wafers. The objective of this research is to prepare iron platinum thin film on silicon on the substrates at different temperatures, characterize the prepared films using atomic force microscopy, magnetic force microscopy, and vibrating sample microscopy, and also X-ray diffraction method. Now, lastly, we investigated the occurrence of double switching mechanisms present in the film on silicon substrate. The contribution to knowledge in this study will show the properties of iron platinum thin films and the cause of the double switching mechanism in iron platinum on silicon substrate. The methodology of this research. The three substrates used in this research were glass substrate, oxidized silicon substrate, and silicon substrate. Glass substrate and oxidized silicon substrate were used as a control experiment, while we want to investigate the occurrence of double switching mechanism on silicon substrate. The substrate were cleaned using ultrasonic device at 90 degrees Celsius for at room temperature for 90 minutes. The substrates were hair cooled or hair dried and glued on the sputtering heater using a silver paste. The glued substrate and the heater were replaced in the sputtering device to form to form a vacuum. The device was pumped down to about 10 to the power of -7 torr. And we could see this is actually the DC magnetic sputtering device when we are pumping down, and at the gun power of 50 milliamps, we were able to excite the electrons or ions from the plasma. You can see the plasma forming a thin film on the substrate surface. And this is the mechanism of operation of the DC magnetic sputtering devices. Now, the research methodology continues here. The prepared thin films were characterized using atomic force microscopy, magnetic force microscopy, vibrating sample magnetometer, and X-ray diffractometer. So for the atomic force microscopy, we use the tapping mode method, where the 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 tip of the cantilever rattles scan over the substrate surface to investigate the topology of the film, and we could see the grains of the grains in figure 4A shows the grains obtained on glass substrate. This is on silicon substrate, and here we have on oxidized silicon substrate. The grains were evenly distributed across the substrate surface, which is actually good for device fabrication. However, the magnetic force microscopy, which was obtained using the Van der Waals, using the magnetic force by raising the tip of the cantilever to a certain height to measure the magnetic force interaction between the tip um, and the synthesized film. We could see it shows a weak magnetic structure on the screen. However, when we increase the temperature, the growth temperature to 250 degrees Celsius, you could see the magnetic domains present on glass substrate, silicon substrate and oxidized silicon substrate. However, for this silicon substrate, you could see the weak structure of brown and white contrast and black also, which shows there's a kind of interaction between the deposited film and the substrate itself. For the AFM, the grains shows uniform distribution. Also, as we increase the temperature to 450 degrees Celsius, we could see different structure, magnetic structure, in figure 6C here, 6B on the silicon substrate. However, for the glass substrate and oxidized silicon substrate, they exhibit similar properties. The white and black contrast shows the positive and negative interaction of the film with the tip of the cantilever. And table 1 shows the increase in the grain size of the film as the temperature increases. Now, the vibrating sample microscope shows the relationship between magnetic moment and the applied field. Now, we subjected the material to an applied field of negative kilorastar to positive, negative 20 kilorastar to positive 20 kilorastar. And at room temperature, the films exhibit similar properties. That is, they exhibit a soft magnetic structure with very low coercivity, which is very good for switching properties and for sensors also. However, when we increase the temperature to 250 degrees Celsius, the film on silicon substrate exhibit different features compared to glass and oxidized silicon substrate. That is, the occurrence of double switching phenomenon starts to emanate from this spectrum here. That is the red spectrum, which is very prominent when we increase the temperature to 450 degrees Celsius. To see the substrate properties of the film and the the hard phase properties of the film. That is, at this region, the film exhibits a soft phase magnetic properties, while at this region, that is the increased coercivity of the film exhibits the hard phase region. For the hard phase region, it shows an increase in area density of the film, where more data can be stored for future use. And the properties of this double phenomenon is one of the reasons why we study this material. Now we did the SRD measurement, which shows the crystal structure and the grain, the crystal size of the material using the Becerra formula. From we did the SRD analysis on silicon substrate and oxidized silicon substrate. And for the oxidized silicon substrate, we could see the presence of the iron platinum peaks prominent at 400 degree 400 plane, and also 110 plane. And however, on silicon substrate, we observe more peaks, although there are a lot of noises on the crystallography. So increase in number of peaks at this region shows likelihood of interaction, magnetic interaction, or granular interaction between the film and the substrate. Our key findings are we are able to deposit iron platinum film on glass, oxidized silicon, and silicon substrate at different growth temperature using DC magnetron sputtering. The AFM analysis shows uniform distribution of grain on the substrate surface, and the magnetic force microscopy shows the likely it shows the likely structure, dual substructure of surface and the art phase structure on the magnetic image. And it shows that the magnetic domains were oriented in the C axis, that is the perpendicular axis. At 23, sorry for that, at 23 degrees Celsius, the synthesized film exhibits a disordered cubic phase structure forming from the VSM analysis. However, at 250 degrees Celsius, an ordered L10, that is the tetragonal phase structure of iron platinum, was observed with an enhanced cohesivity, which increases the area density for more data storage. The doubles the double phase of iron platinum silicon on silicon substrate were ascribed to the cubic phase and the L10 tetragonal phase with an enhanced cohesivity. The SRD findings shows the presence of polycrystalline thin film with 1-on-1 orientation. On both substrates, that is the silicon and oxidized silicon, the ordered L10 phase was discovered at 001 axis. However, new spikes or peaks were observed in the crystallography phase of iron platinum silicon, which were absent on the oxidized silicon substrate. As such, we conclude that there is likelihoodness of interfacial diffusion between the film and the substrate. As a result, the iron platinum substrate shows double switching properties of surface and art phase structure. These are some of the references that guided us throughout the research. We want to acknowledge the effort of financial support of National Science Foundation for funding this research. Also, a special appreciation goes to Towson University Research Laboratory for the SRD measurement. Now, for further studies or future works, we aim to use SPS, this is the X-ray photoelectron microscopy and spectroscopy, and EDX, energy dispersive spectroscopy, X-ray spectroscopy, to investigate the chemical bonding and the elemental properties of the grown film, which will actually reveal whether the deposited film is iron platinum silicon thin film or iron silicon thin film or platinum silicon thin film. Thank you for listening. And here is my contact um, email for further inquiry. Thank you.